Welcome to section 14.3. Don't forget to take notes and complete everything along with me and on your own. This section is pretty vocabulary heavy. And we are going to be talking about congruence. And we've talked about congruence before. It's a mathematical term for saying that two geometrical objects are identical. And we define congruence in terms of rotation, translations, reflections, which we already studied. So what information about two shapes will guarantee that they're congruent? And it's interesting because triangles are really different than other shapes. Triangles are structurally rigid, which we're going to look at, and the criteria for the congruence of triangles is related to their structural rigidity. So the distinction between triangles and other polygons explains some standard practices and actually how we build construction and architecture and buildings around us. So even though the study of congruence may seem really abstract, it actually has a ton of practical applications. So informally, we say that two shapes are congruent if they are the same size and the shape is congruent. But what if we have two shapes or designs drawn on semi-transparent pieces of paper? How would we determine whether they are congruent? So let's do an exploration here. So for this one, there's a download that you can grab, or maybe you want to cut it out of the slides, and you're just going to move these two triangles out in front of you and see if you can determine if they're identical copies. So to check if those two paper shapes are congruent, we would probably slide one shape over the other, rotate it, see if they match up. We might flip a paper over and try it again. So basically, to check if two shapes are congruent, we would use translations, rotations, and reflections. So we define congruence formally in this way. Two shapes or designs in a plane are congruent if there is a rotation, reflection, translation, or combination that takes one shape onto the other. And this is something you already knew because you did it in the last exploration. To see if they're the same, you would move it around and see if they line up. So in design and construction, people often need to describe how to make an exact replica of an object. So what information would be enough to specify? And that's what we're going to look at in the case of triangles and then quadrilaterals. This is a really fun exploration if you can get these, and the straws help you to actually get some rigidity. So I encourage you to do this to really make sense of what is enough, and then press play when you're ready to move on. So in this one, grab your compass, grab your ruler, or hop into GeoGebra, which is a great tool, and build these triangles and see what happens. And then once you build them, if they're possible, try to draw a second triangle that meets the same conditions and determine if they're congruent. And then press play when you've completed all of that. So in the explorations, you saw that some pieces of information are enough and some are not enough. Sometimes there is more than one distinct triangle that fits the given information, and other times there is no such triangle. So a set of information that specifies a unique triangle is often called a congruence criterion because any two triangles that fit that information are exact replicas or congruent. So now let's study the three congruence criteria for triangles, and we'll contrast these with information that does not specify a unique triangle. So first, let's just talk about like reading triangles. So this may seem silly, but let's just hop in here. So again, this is a side, and a side, and this is an angle, angle, angle. So if we were to talk about a side, angle, side, what we're talking about is the side and the angle inside of it, and then the side around it. If we were to talk about side, 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 we would be talking about all three sides. If we were to be talking about angle, side, angle, it would be an angle on either side, so it would be angle, side, angle. So it's not just any place, right? It would be the words that you read tell you around how to read it around the triangle, all right? So let's start with side, side, side. If you form a triangle, this was the exploration, by threading a 3, 4-inch, and 5-inch straw together in a quadrilateral, you'll see that the triangle is rigid where the quadrilateral is floppy. So if you didn't have a chance to do it, you can see here that with the quadrilateral, you can press it down. You can make it turn into all different kinds of quadrilaterals, where if you built that triangle, that thing is staying put. It's not changing. So that's to say that the sides cannot be moved independently, but the quadrilaterals can. And so what that means is that those three side lengths made a unique triangle that makes no other triangle. And that is the side-side-side congruence. And it only works for triangles, not quadrilaterals. 4 sides is not enough. Take a look at this folding rack. Many of you may even own this. Look here, we've got quadrilaterals, but at the bottom, we've got a triangle, and at the top we've got a triangle. What happens when you unclick the top and you've just got a bunch of quadrilaterals? It falls down because the 3 sides of the triangle create a structural rigidity, and that's why you actually see that in construction. All right, so let's go to the congruence. Here is the congruence statement. Given a triangle that has side lengths A, B, C, it's congruent to all other triangles that have the same side lengths. All right, so this is the side, side, side. If I give you 3 sides, there's only one triangle that builds that way. That's a unique triangle. And this is the geometrical proof of how that works, that there's only one triangle that can be built. And you might be saying, oh, here's another one. But remember, it's just being reflected. And if we were to unreflect that, it would be the same thing. Will any 3 lengths, so now I said 3 sides, I'm going to make a triangle, but is that really true? If one side's length is greater than the sum of the lengths of the other 2 sides, it won't close up. So what this is saying, and this is actually saying the opposite thing of these words here. So what this is saying is that if one side is greater than the sum of 2 sides, then it won't work. What this is saying is that we need one side to be less than the sum of the other 2 sides. Sometimes reading these can be a little bit confusing there. But basically what they're saying here is that not all 3 side lengths will build a triangle. This side length here is too long. It's in fact longer than B plus C. This longer side is greater than B plus C, so it won't work. Let's look at another congruence criteria. This one is angle, side, angle. So again, the way we read this, here's an angle, here's a side, and here's an angle. So if we see that and let's go back to this for a moment. If we see that we're given the sides, this is 3, 4, 5, and we're given another triangle that's 3, 4, 5, we can say that they're congruent by the side, 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 because they all have the 3 same sides, and we know that that only makes one triangle. The same thing can be said for angle, side, angle. If we're given triangles, and maybe they're flipped, right? We don't know. And we're given this value, and this value, 40, maybe 10, and 60 degrees. And then over here, we're given, oh, I drew it the same way. Oh my goodness. Sorry to draw. There we go. Okay, here we're given 60 degrees, 40 degrees, and 10. We're given an angle, the side, and the angle. And so we can say that these 2 triangles are congruent by the angle, side, angle. And lastly, we've got the side, angle, side. So if we've got 2 triangles, I'm going to try to, and side, angle, side, which means the angle is between those 2 sides. So maybe we know this is 20, this is 25 degrees, and that's 30. And then over here, we've got 20, 25 degrees, and 30. We could say that these are congruent. And if you were to kind of shift this around, you could rotate this one or reflect it maybe to get it to match up. So side, angle, side. And this one kind of just describes the reason why it's valid. Let's do an example. Actually, okay, yeah, we'll do an example. Which property, if any, should be used to show that the pair of triangles is congruent? So let's take a look at what we're given here. We're given a side, and then an angle, and then another side. So what do we notice though? We've got 16, 23, and 25. These are not congruent because they don't have the same angle. So these are not congruent. Name two triangles that are congruent by angle, side, angle. So let's kind of line these up by their, okay, so we've got A, B, C. Okay. And then we've got D, E, F. And then E is this is that, D is 2, and DF is 2. And then we've got, and I'm only doing this because it helps me think about it if they all kind of are looking the same. GJ is 2, G is 2, GH is 1. Okay, so when I look at these, they're clearly giving me side, angle, side. All right, or I could think about it as they're giving me angle, side, angle. Either way, let's look for what's congruent. And I see here GH is, that should be 1. I see here that I can prove that these are the same by angle, side, angle, or I could prove that they are the same by side, angle, side, side, angle, side. So I can say that DEF is congruent right there. And when we come back, we'll look at some more examples.